like crazy.
So today I'd like to talk about the second big instrument for measuring water potentials. The first one was thermocouple psychrometer, or chilled mirror psychrometer, for measuring water potential. And the other instrument that people use is the pressure chamber. So that's what this thing is. And it's just what it sounds like, a pressure chamber. A chamber that you can increase the pressure on. All right, and it measures water potential. Can you believe it? How does that work? That's what I want to talk about today, how that works. Okay, so pressure chamber. It used to be called the pressure bomb more frequently, but now people shy away from those words, and they call it a pressure chamber. And it measures total water potential. It can also be used to make a pressure volume curve, which is what this thing is. And from the pressure volume curve, we can get information about not only the total potential, but the pressure potential and the osmotic potential and the apoplastic fraction and some other things. And that'll be the subject of our next meeting, which will be a week from today, Tuesday. No class this Thursday. We have an Ameriflux site in the Sandhills at Gudmundson Ranch, and our CO2 sensor quit working, so I've got to go out there. So that's why no class Thursday, but we'll meet again a week from today, Tuesday. And I'll talk about this pressure volume curve. But first we have to figure out what the pressure is. This one was made at Precision Machine here in Lincoln. This one is, some company sells that thing, so this is a little more rustic looking. Okay, so here's some references. This is if you're using pressure chamber in your thesis or something. Everybody else cites this reference, Scholander. Sometimes this is called the Scholander chamber. And these people worked at Woods Hole, not Woods Hole, Scripps Institute of Oceanography in California, in San Diego. And they used the pressure chamber. Okay, so they published in the Proceedings of the National Academy hydrostatic pressure and osmotic potentials in leaves of mangroves and some other plants. It's the first modern reference, 1964, modern reference for the pressure chamber. Ritchie and Hinckley have a nice review article in Ecological Advances in Ecological Research on the pressure chamber. And Ted Chow again in this Irrigation of Ag Crops. I didn't bring the book in because this is heavy enough, but that big fat green book that I've brought in several times has a good description of the pressure chamber in his chapter called Measurements of Plant Water Studies. Okay, so I said modern, right? 1964, modern. I mean, my little sister is older than that, right? It's got to be modern. But they weren't the first ones to use a pressure chamber. I think the first ones, amongst the many people that have used the pressure chamber, amongst the first ones was this group led by Henry H. Dixon at the end of the 19th century, beginning of the 20th century, used a vessel that he could pressurize because he was interested in studying the composition of the sap of plants. Right? And by sap, pretty much, well, what's in the xylem, I think. And so he needed a way to extract that sap from the plant without getting everything else mixed up with it. And so he developed this vessel, a glass vessel that you can see here, that he would put a leafy shoot in and connect it to a high pressure source and increase the pressure, and then the stuff that bubbled out the end he would collect in a little vial, and then he could analyze it and do whatever he wanted with it. Right? So it was a way of obtaining his sap samples. So you know what happened was the chamber exploded. was made out of glass. And if you increase the pressure enough, it exploded. And so this apparatus fell out of favor with researchers, right? Nobody wanted to use something that blew up, right? It's fun to read, well, fun. It's interesting to read this 1895 paper. Okay, so this is in the library. You have to go to a storage place. The Proceedings of the Royal Society of London, Part B, 1895, they published a paper called On the Ascent of Saturn. It's interesting to read this. An accident to the apparatus, the stopper beneath, being blown out during the second hour prevented a weighing being made. Right. Okay. No further experiments were made with this apparatus as it unexpectedly burst in the course of the next experiment. Fortunately doing no harm, but putting a stop to further experiments. Right? So I like reading this because it's a great paper, but you'd be hard pressed to publish these sentences in your paper today in a journal, right? No, you can't say stuff like that.
If that happened today, like, you wouldn't publish the experiment.
Right, you'd say, oh, yeah, you wouldn't even talk about that. Yeah. I mean,
That's also kind of.
but it's it's useful information to have, right?
Don't do it out of class.
Yeah,
It's part of your repeatable materials and methods.
yeah, there we go.
Repeatable, yeah.
Yeah, and Scholander's group, what they did was, that's exactly what they said. Don't make it out of glass, make it out of steel, right? So it can't blow up. And that's what they did. But it took from 1895 to 1964 before this idea was resurrected. Anyway. Okay, well, you can read it. Okay, so the pressure chamber is exactly that. It's a chamber that we can increase the pressure on. Increase the pressure over atmospheric pressure. And that's what this gauge tells us. It's a chamber. You connect it to a source of high pressure. You increase the pressure. This gauge tells you how much above atmospheric pressure you have inside the system. And that's what this thing is. So here's the chamber, here's the gauge, here's the connection to a source of high pressure. Usually a tank of nitrogen, sometimes compressed air is used, but usually nitrogen. Okay, and there's a valve on it here that can control the rate of the increase of pressure, and then an exhaust valve over there. But it's really a simple system, a simple device. How can this possibly measure pressure? I mean, water potential. Well, water potential is pressure. They're related. Here's how you use it. I'll describe how it's used first, and then get into why it works, or the ideas behind it. So if I want to measure the total water potential of a leaf of a plant, I go up to the plant, I take some plastic wrap or foil or something and cover up the leaf. That's to stop or to reduce the transpiration rate from the leaf, because I'm going to cut the leaf off the plant. As soon as the leaf is cut off the plant, if it wasn't covered up, it would be losing water by transpiration. And I want to minimize that water loss. So you cover the leaf up and you cut the leaf off. Then you take the leaf over to the pressure chamber, stick it in here, still covered up, with the end of it poking out the top. Now this cap is for a grass type leaf. Here's a cap for a leaf with a distinct petiole. So there's different kinds. But put that inside the chamber, cover it up. Covered up with the end of the leaf sticking out. All right. Then I slowly increase the pressure inside the chamber. Slowly. And even more slowly once the end point is reached. What's the end point? Well, as this pressure is increasing, I watch the end of the leaf from the side, not from the top, from the side, and increase the pressure slowly. And especially watch the vascular bundles in the end. And eventually, as this pressure increases, the stuff in the xylem is going to come right back up to that cut surface. When the sap in the xylem is right at that cut surface, that's called the end point. And then I make a note of what pressure that is on the gauge. Now I'm down to 0 waters. Oh, there it is. Still got one. That pressure, the negative of that pressure on the gauge is the total water potential of the cells. And that's it. Then it can stop and exhaust the pressure, open it up, put another leaf in and make another measurement. That's how it's used. So it's really simple. How does this work? Well, I'm telling you that's the way it is. You can't argue with it. That's it. The negative of this gauge pressure is equal to total water potential of the tissue. This gauge here reads in pounds per square inch, so you'd have to convert that to megapascals and whatever.
So when you're saying the negative, you're just, so if it's 50, it's just negative 50.
Yeah, like I think it's 147 or 145 or something equals 1 megapascal. So if it's reading 145, let's say, the total water potential in the leaf is negative 1 megapascal. I mean, the total potential is going to be negative.
Okay.
In the leaf. And this pressure is positive, so you just have to make it negative. That's what this is.
Okay.
Yeah. All right? Do you just accept that on faith? Or do you want to be convinced? If you say just accept it, okay, then we can leave early today. I'm just joking, you can't leave early today. Okay. So this device is commercially available, right? You can buy it. Here's a company in Australia that makes them, ICT International. So I just checked this today, and it works in my office. So let's just look at it. Here's their website, part of their website. Water potential, products, pressure chambers. Here's a whole slew of pressure chambers, and you can see the different kinds. Yeah, I mean, they have a chamber, they have a gauge, they have some valves. This one is kind of interesting. It's a pump-up chamber. It's limited to water potential is close to 0, I think. -0 to -2 megapascals. But it's nice in that you don't need a high pressure tank. It's just got like a bike pump, a tire pump for your bike, and you pump it up like that. So, you can go out in the middle of nowhere and use it without hauling a big tank of compressed air. Right? So have a look at this. There's a lot of information here. For example, here's this pump-up chamber. More information, PDF, tells you about it, all kinds of stuff. So ICT International. As I said before, different kinds of tops. This one was made for leaves like soybean that have a distinct petiole. And